Today's session, we're going to look at aromatic compounds, and which is part of the organic chemistry topic. So we're going to be starting off this topic, aromatic compounds, by looking at benzene. And benzene is an aromatic compound. So this is benzene. Benzene has the formula of C6H6, and we say it has a planar cyclic structure. By that, what we mean is it has 6 carbon atoms, and these 6 carbon atoms are joined together in a flat ring. So planar meaning it's flat, cyclic meaning it's circular, and it's just these 6 carbon atoms that are joined together in this flat ring. And so what happens in benzene is each carbon atom forms a single covalent bond. So each carbon forms a single covalent bond to the carbons on either side and to one hydrogen atom. So what basically ends up looking like is you can see it here showing the orbitals. But if I drew it here, what you've basically got is this sort of formation, that each carbon atom forms a single covalent bond to the carbons on either side of it and to one hydrogen atom. And then obviously each one has a hydrogen atom coming off of it. The final unpaired electron on each carbon atom, because as you can see, each carbon could make one more bond. And so that final unpaired electron on each carbon atom is located in the p orbital. And what this p orbital does is it sticks out above and below the plane of the ring. So you can see that underneath here. So let's just get rid of that. So here we've got each of our carbon atoms, which are red circles, hydrogens coming off them, which are purple. And then we've got the electrons in the p orbitals, which you can see here. We've got p orbitals above and below the plane of the ring. The p orbitals on each carbon atom combine to form a ring of delocalized electrons. So we can see it here. Each p orbital combines together and we get this ring of delocalized electrons, and we have that on top of the plane and below the plane. And a reminder that delocalized means the electrons don't belong to a specific carbon atom, but they're shared between them all. So here, the unpaired electrons would be per carbon, but they join together to make this ring of delocalized electrons, and we've got those 2 rings. All of the carbon-carbon bonds in the rings are the same, and they are the same length. The length of these carbon-carbon bonds are 140 picometers. And this lies in between the length of a single carbon-carbon bond, which is normally, so these are the bonds in the benzene. So a normal single carbon-carbon bond would normally be 154 picometers, and a carbon double bond would be 135 picometers. So as you can see from this image, benzene is a planar flat molecule. It's got a ring of carbon atoms with a hydrogen sticking out all on a flat plane. So how you will normally see benzene drawn, I'm just going to draw that out for you now, is you'll often see benzene drawn like this. This is my best attempt at drawing benzene. I do apologise. I'm going to clear that was not the best. So that's the benzene as best I can draw it. And in the middle, we've got the circle. That circle, whenever you see benzene drawn like this, that circle is representing that delocalized ring of electrons. You might occasionally see it drawn like this. And when it's drawn like this, we don't have it looks a little bit confusing because some people think that might mean we've got alternating single and double bonds between the carbon atoms. That's not true. Scientists used to think this was a structure, and their way of drawing it has just stuck around. So we actually have this delocalized ring of electrons. We don't have alternating single and double bonds, but scientists used to think that. So occasionally you may still see benzene drawn like this, and their way of drawing it has stuck around. But remember, we still got each hydrogen attached. So if we drew it out fully, it would look like this. Oops. Let me just put it out. Draw in a better place. So it would look like this. Now, so we've got hydrogen off each one. And we've got our delocalized ring of electrons in the middle. So let's look at this delocalized ring of electrons in the middle a little bit more. So this delocalized ring of electrons that we've got in the middle of benzene makes benzene really, really, really stable. And it makes benzene more stable than a theoretical compound, which we're going to look at now, which is called cyclohexa 1,3,5 triethene. No, not triethene. That was me going wrong. Triene. Me thinking about two things at once. Triene. And this theoretical compound, cyclohexa 1,3,5 triene, would be made up of those alternating single and double bonds. So how we used to think benzene might be made. So where we've got those alternating single double bonds like this. Benzene's more stable than that. So that's how we sort of worked out about this delocalized ring of electrons. So we can see this and prove this by comparing the enthalpy of hydrogenation for benzene with the enthalpy change of hydrogenation for cyclohexene. So cyclohexene, which you can see on the screen here, cyclohexene, has one double bond in it. So when it's hydrogenated, the enthalpy change is minus 120 kilojoules per mole. If benzene had 3 double bonds, we would then expect benzene to have an enthalpy change of minus 360 kilojoules per mole. So this is our predicted for benzene if benzene had 3 double bonds. Okay, so if we predicted that, we'd say it would have minus 360 kilojoules per mole hydrogenation. But the experimental enthalpy of hydrogenation of benzene is actually minus 208 kilojoules per mole. So it is far less exothermic than expected. So it's less exothermic than we were expecting it to be. So energy, we know, is put in to break bonds, and energy is released when bonds are broken. So therefore, more energy must have been put in to break the bonds in benzene than would be needed to break the bonds in a theoretical cyclohexa 1,3,5 triene molecule. And that's basically this theoretical molecule is what it would have been if benzene had basically those 3 double bonds and 3 singular bonds. So this difference, what this difference does is it indicates that benzene is more stable than cyclohexa 1,3,5 triene would be. And this is all thought to do with that ring of delocalized electrons that we have got inside benzene. So rather than having those alternating double single bonds, it's this delocalized ring of electrons that creates this stability. So aromatic compounds, I said this topic was on aromatic compounds. We talked about benzene. Aromatic compounds are derived from benzene. So compounds that contain a benzene ring, and we call anything that has this basic benzene structure with that delocalized ring of electrons inside it, a benzene ring. They're called arenes or aromatic compounds. So another name for aromatic compounds are arenes. So you might see them being referred to as arenes, or you might see them being referred to as aromatic compounds. And there is two ways for us to name arenes. So here are some examples. So some are named as substituted benzene rings. So for example, this one, we've added a chlorine to our benzene ring, so it would be chlorobenzene. Added a nitrogen. So we've got nitrobenzene. And then our final one, we've got two methyl groups added. We count the carbons that they're on. So we've got a 1,3 dimethyl benzene. So that is one way of naming arenes, is we substitute, names are substituted as substituted benzene rings. The second way we can name them, we name them as compounds with a phenyl group attached. So for example, we've got phenol or phenylamine. So that is two ways of naming aromatic compounds. So that's really important to know if you're asked to name an arene. So arenes undergo electrophilic substitution reactions. So the benzene ring is an area of high electron density. That makes sense. We've got this area of delocalized electrons, and this benzene ring is an area of high electron density. So draw out the benzene ring as best as I can. So the benzene ring is a region of high electron density. So we've got high electron density here. So any arene that contains the benzene ring, or arenes contain the benzene ring, got that high electron density. And as we know, any areas that have high electron density, they attract electrophiles. Because our benzene ring is stable, it doesn't undergo electrophilic addition reactions. Okay, so because this ring is stable, it does not go through electrophilic addition. Electrophilic addition reactions would actually come in and they would destroy that ring of delocalized electrons. So instead, it undergoes electrophilic substitution reactions. And in this situation, what happens is one of the hydrogen atoms, so one hydrogen atom or another functional group on the ring, is substituted for the electrophile. So you need to know two electrophilic substitution mechanisms for benzene. I'm going to go through them now. One of them is called Friedel-Crafts acylation, and the other, if I can write it, there we go, is nitration reaction, which we will also go through. So we're going to go through the I missed my R off on Friedel. Our Friedel-Crafts acylation first, and then we'll go through nitration reactions. So these are both electrophilic substitutions. So Friedel-Crafts acylation reactions produce phenyl ketones. So that's really important to know. And again, I'm just going to put in brackets up here. This is an electrophilic substitution reaction. So many useful chemicals such as dyes and pharmaceuticals contain benzene rings. But as we said, benzene is really, really stable, so it's really unreactive. So it can be really hard to make chemicals that contain benzene. When we use Friedel-Crafts acylation reactions, what we come in and do is we add an acyl group. So we're going to add an acyl group, which you should remember is RCO to the benzene ring. And what happens is, so an acyl group is added to our benzene ring. And once that acyl group has been added, then the side chains can be modified using further reactions to make those useful products. An electrophile, as you know, has to have a really, really, really strong positive charge to be able to attack the stable benzene ring. Most electrophiles aren't polarized enough to be able to do this because the benzene ring is so stable. But some can be made into stronger electrophiles using a catalyst called a halogen carrier. So we have to make an electrophile stronger. So we have to make a stronger electrophile. And we do this by using a catalyst called a halogen carrier. Friedel-Crafts acylation uses an acyl chloride as an electrophile. So our electrophile is going to be our acyl chloride as an electrophile and a halogen carrier as well. And the halogen carrier often, so that would be our electrophile. Often the halogen carrier in this situation would be something like aluminum chloride. So let's have a look at how a halogen carrier then can make an electrophile stronger. Have I bothered putting that up? No. So let's pop it here. So let's draw this out. Let's draw our acyl chloride out. So acyl chloride will look something like this. We've got our R group, our carbon, double bonded to oxygen, and chlorine down here. Let's add on our charges. Remember that that carbon is going to be slightly positively charged, and that chlorine is going to be slightly negatively charged, and that is our acyl chloride. Remember as well that that chlorine is going to have a lone pair of electrons on it. And let's add on our halogen carrier now. So let's add it in here. We've got AlCl3, and that is our halogen carrier, which is a catalyst. So our AlCl3 accepts that lone pair of electrons from the acyl chloride. So that's the first thing that happens. It accepts that lone pair of electrons. So these are going to go along to here. And as the lone pair of electrons is pulled away from the acyl chloride, the polarization in the acyl chloride increases. So, So as this lone pair of electrons is getting pulled away by the AlC3, which is a halogen carrier, and the polarization inside our acyl chloride increases. And what it does is it then goes on to form a carbocation, which we've come across a lot in the past. So we've now got a carbocation forming. So that polarization increases and we make the carbocation. This is what our carbocation will look like. So we've got our R group, singular bond to our carbon, double bond to oxygen, and now our carbon has that permanent positive charge. And so this is our carbocation. cation. This makes it a much stronger electrophile because it's now a carbocation, and it gives a strong enough charge to react with benzene ring. And because obviously our halogen carrier is accepted that lone pair, and from the chlorine and pull the chlorine away, I'm just going to show what that will now look like. And that would look like here, it would now be obviously AlCl4 minus. So that is, that's how our halogen carrier makes the acyl chloride electrophile a lot stronger. So let's have a look now at how the electrophile is substituted into the benzene ring. So how this carbocation of the acyl chloride is going to be substituted into the benzene ring. Now this mechanism has 2 steps. So this is our first step here. So what happens here is the electrons that we've got in the benzene ring are attracted to that positively charged carbocation that we've just made. Okay, so the electrons here are attracted to that positively charged carbocation. And 2 electrons, and I'm just going to write this underneath so that we're sure about this. So it's 2 electrons from the benzene bond with the carbocation. What this does is this partially breaks a delocalized ring and gives it a positive charge, which you can see here. So we've got those 2 electrons bonding with the carbon, and we've got this partial breakage now of the delocalized ring, and it's got a positive charge. It's not fully broken, but we've just got that partial break. So that's the first step. Now, second step, our negatively charged AlC4 ion, so this ion that we created here when we were adding the halogen carrier and making our electrophile stronger, comes into use. So this negatively charged AlCl4 ion, which you can see here, is going to be attracted to the positively charged ring because it's a negatively charged ion. It's going to be attracted to our positively charged delocalized ring. What happens is 1 chloride ion on the AlCl4 minus ion breaks away from the aluminium chloride ion, and it bonds with the hydrogen ion. And it's the hydrogen ion that has been formed because of this delocalized ring. This removes the hydrogen from the ring and forms hydrogen chloride, which you can see here. And it allows the catalyst to reform. So the catalyst reforms, we have that delocalized ring reforming. And so now we've got a phenyl ketone. So we've got that acyl group now fully added on, our delocalized ring fully formed, and now we've gone back to our aluminium chloride as our halogen carrier reforming. Catalyst reformed is there. We've got hydrogen chloride here, and we've made our phenyl ketone. When we're doing these reactions, some conditions that we need to make sure that we're adhering to is that it is heated under reflux in a non-aqueous solvent. An example for that would be dry ether. And that needs to happen for the reaction to occur. As I said, there was another way of making aromatic compounds, and that is nitration, which we'll look at now. Nitration, we use this in the manufacturing of explosives and dyes. And in this situation, we're going to warm our benzene. So if you warm benzene, with concentrated nitric and sulfuric acids, so we're going to warm our benzene with concentrated nitric and sulfuric acids, you get something called a nitrobenzene. In this situation, our sulfuric acid is acting as a catalyst, and it helps to make the nitronium ion, which is the electrophile. So I'm just going to write out the whole equation for this here. So we're going to warm benzene with concentrated nitric and sulfuric acids. I'm going to get our nitrobenzenes. So let's draw this out. So we've got HNO3 and H2SO4. So then we get H2NO3 plus and HSO4 negative. So that helps us to make that nitronium ion, which is going to be our electrophiles. So then what happens is, let's change that. We will get H2NO3 positive. We get that nitronium ion here, which is going to be our electrophile, and water. So this underneath is the electrophilic substitution mechanism. Sulfuric acid was our catalyst, and that helped us make that nitronium ion. So here's the electrophilic substitution mechanism. As you can probably see, as I'm going to go through it, it's really similar to the Friedel-Crafts acylation that we've just been through. So our nitronium ion, which we've just made here using our sulfuric acid catalyst and our concentrated nitric acid, we've warmed them together. We're going to then use the nitronium ion, and it's going to come along and it's going to attack the benzene ring because that's our electrophile. Then what happens is an unstable intermediate forms. We've got that breakage of that delocalized ring of electrons. And then what's going to happen is that hydrogen ion is going to then be attracted to the delocalized ring of electrons. We lose that hydrogen ion. And then we've got the formation of our RE. So what happens here is the hydrogen ion reacts with the HSO4 negative to reform with the catalyst. So it helps reform our catalyst all over again. If you only want one NO2 group added, which is mononitration, you have to keep the temperature below 55 degrees. So I'm just going to add that on here. So if we only want one NO2 group added, so mononitration, the temp needs to be below 55 degrees Celsius. Above this temperature, you'll get lots and lots of substitutions happening. So nitration reactions are really useful. I'm just going to draw one out for you. So we've got CH3. Okay, so nitro compounds can be reduced to form aromatic amines, and that's something that we'll look at in the next session. So we can reduce them, can be reduced to amines, and we'll look at this in further detail later on. So they can be further reduced to make amines, and when we do that, these are used to make dyes and pharmaceuticals. Or some nitro compounds can be used as explosives. So this is an example of an explosive known as TNT. So 2,4,6 trinitromethylbenzene, so TNT. And that is an example of e.g. TNT, and that is TNT here. Let's go through some exam questions now based on this. So a halogen carrier, such as aluminium chloride, is used as a catalyst in the reaction between the benzene and ethanol chloride. What you're asked to do is you're asked to describe the conditions needed for this reaction. So we've got a halogen carrier, got an example of it, and it's being used as a catalyst, and that we're being told what it's catalyzing, what two things it's catalyzing. Describe the conditions needed for this reaction. So we're describing conditions, and that's 1 mark for the reaction. So the conditions that we would need is we would need it to be carried out in a non-aqueous solvent. So an example would be dry ether. And it would also need to occur under reflux. You're then asked on the same question to explain why the halogen carrier is needed as a catalyst for this reaction to occur. Now, that's all about that stability of the delocalized ring. So because the benzene is really stable, our acyl chloride molecule is not polarized enough. It's not strong enough electrophile to attack that benzene ring. So because benzene is really stable, our acyl chloride molecule is not polarized enough or strong enough to attack the benzene. That will get you the first mark for that. So you've explained what has happened. Well, acyl chloride can't work on its own just as an electrophile. Oh, I have forgotten that word. It's not polarized, not strong enough electrophile to attack the benzene. 1 mark. Second mark, we're going to explain why then we need that halogen carrier. So the halogen carrier makes the acyl chloride electrophile stronger. The halogen carrier makes the acyl chloride electrophile stronger. That would get you that second mark for that question. To then get that 2 marks. And finally, you're asked for this question to draw the structure of the electrophile that attacks the benzene ring. And that obviously, that electrophile isn't just acyl chloride, it needs to be the acyl chloride after it's gone through being made into a stronger electrophile by the halogen carrier. So this is what it would look like, remember. So we're being told that our halogen carrier is going to be aluminium chloride. So this is what it would look like. Remember, at this point now it's a carbocation, so we've got that positive charge on our carbon with the oxygen there, and that will get you 1 mark. Our second question, we've got an electrophile substitution reaction of benzene, and that's summarized in the diagram. So we can see benzene, and we're being told that B plus C gives us that product, which is being classed as A, and then there's some conditions that need to be met. So the first thing you're being asked is to name the product A. Well, that's where we need to remember how to name arenes. So we've got an aromatic compound, so we've got benzene. We've added a nitrogen group, so the halogens of nitrogen to it. So therefore, A is a nitrobenzene. Oops. What's happened here? So A is a nitrobenzene. So we've named the product A. And then it asks you to name the reagents B and C. Well, if we're going through this process, is, as we said, would be a nitration reaction. And so if it's going through a nitration reaction, the reagents that we need, so B and C, it doesn't matter which way around B and C are. So B and C, those reagents have to be concentrated nitric acid and concentrated sulfuric acid. And then finally, it wants us to say what those conditions are. So it needs to be warm. And because we've only got one nitrogen group added on there, so it's mononitration, and it needs to be no more than 55 degrees Celsius. Then we're asked to write equations to show the formation of the electrophile, because remember that electrophile needs to be made into a stronger electrophile using the catalysts. So here we go. Let's have a look at this. So we're going to put down both of our reagents. So concentrated nitric acid and concentrated sulfuric acid. I'll get you first mark. That's the first equation that you need. And then using this, we're going to then get our second equation. Because then we get our electrophile forming, which we've got now here. This would be our electrophile. And obviously water as a byproduct. And then finally, you're asked to outline a mechanism for this reaction. So using that electrophile you've just identified here. So let's draw that benzene ring on straight away. And electrons from benzene ring are going to be attracted to our electrophile. When that happens, we get that breakage of the benzene ring. And a hydrogen ion forms. That hydrogen ion is attracted to the positive charge of a delocalized electron ring. And then finally, I'm going to end up going over there, so I'm going to have to write down here. And that hydrogen ion breaks off. And so then we get the formation here of our final product with our hydrogen ion. And that is aromatic compounds.